So, in the last few lectures we were examining the laminar flow in a pipe. We had got the friction factor as a function of Reynolds number by first solving the momentum conservation equation at steady state. Okay, if you recall, the equation was of the form minus dp by dx is equal plus 1 by r d by dr of r d tau r times tau xr is equal to 0, and we know that dp by dx is a constant in this case. Therefore, we got tau xr is equal to minus dp by dx into minus r by 2. Okay. That was the shear stress, and the shear stress at the wall was given by tau w is equal to minus dp by dx into the radius of the pipe divided by 2. And the magnitude of the wall shear stress was equal to minus dp by dx into r by 2. Okay. This is the stress that is exerted by the wall on the fluid, which is in the minus x direction. The stress exerted by the fluid on the wall is in the plus x direction, okay, in this particular case. And we had solved for the velocity profile, which was a parabolic profile, and then determined the average velocity, which was equal to 1/2 of the maximum velocity, calculated the friction factor from the relationship between the velocity profile and the by the relationship between the average velocity and the pressure gradient. Okay. Last time we were looking at the friction factor for a power law fluid in a pipe. A power law fluid which has this as the constitutive relation. Okay. Note that the stress has the same sign as the velocity gradient in this case. Okay. The reason for the modulus is so that the stress has the same sign as the velocity gradient. And this contains two parameters, a power law index n and a flow consistency index k. The boundary conditions are the same as those for a pipe flow for a Newtonian fluid. Velocity has to be 0 at the wall, and the velocity has to go through a maximum at the center where the slope is equal to 0, so that the slope is uniquely specified at the center. Before we proceed, let us just examine what is the dimension of this flow consistency index. Okay. The dimension on the left side is the dimension of the stress. Okay. Mass, length inverse, t power minus 2. Okay. That is the dimension of the stress, m L inverse t power minus 2. Force per unit area, force is mass times acceleration. This has to be equal to the dimension of the flow consistency index. Okay. The dimension of the flow consistency index times the dimension of dvx by dr. dvx by dr, velocity divided by a distance, which is inverse time. Okay. So, this will be t power minus n, okay, which means that the flow consistency index has to have dimensions of m L inverse t power 2 minus n, I am sorry, n minus 2. Okay. That is the dimension of the flow consistency index. Okay. So, I think the last time I had written it as n minus 1, that is not correct. So, this should be n minus 2. Now, how do we get a Reynolds number from the flow consistency index? Okay. We had solved this before, but I will just give you the final result. This is equal to rho V average power 2 minus n times d power n by kappa. Okay. And you can verify that this is dimensionless. Okay. So, for example, the dimension of this Reynolds number is equal to density, which is m L power minus 3, mass per unit volume. Okay. the average velocity L T inverse power 2 minus n into the length power n divided by the dimension of the flow consistency index, that is m L inverse T power n minus 2. Okay. And you can see that the mass dimensions will cancel out. The length dimensions, in numerator have L power minus 3 and L power 2 minus n and L. Okay. So, this is 2 minus n plus n gives you 2, minus 3 is minus 1, and therefore, in the denominator also have minus 1, and these will cancel out. T inverse power 2 minus n, okay, which is T power n minus 2, which is the same as that in the denominator. Okay. So, this is dimensionless. So, therefore, this is the definition of the Reynolds number for a power law fluid. Okay. The friction factor was equal to tau w, okay, the magnitude of that by rho V average square by 2. Okay. We know for a laminar flow it has to be proportional to 1 over Reynolds number. Okay. In this case as well it has to be proportional to 1 over Reynolds number. Okay. So, I can write this as 1 over Reynolds number, that is rho V average power 2 minus n, okay, into d power n into tau w divided by k into V average power n, okay, into d power minus by 2. Okay. You can easily see that in the denominator the k's will cancel out in this case. Okay. The k's will cancel out in this case. Okay. The V average power 2 minus n times V average power n in the denominator just gives me V average square. D power n times d power minus n just gives me d. Okay. And therefore, this is equal to the first expression that I had on the left side, except that this is now of the form 1 over R e into tau w by k V average power n d power minus n by 2. The advantage of doing it this way is that I now have an expression for V average power n. Okay. This is the expression for V average, and therefore, if I take the nth power of that, okay, I will get 1 over R e into tau w is minus dp by dx into r by 2 divided by V average power n, which is okay, tau w is equal to into r by 2, okay, divided by kappa, okay, the flow consistency index, into V average power n. Okay, V average is given here. Okay. So, this to the power of n is going to be equal to n by 3n plus 1 whole power n into r power n plus 1 into and the advantage of writing it this way is that this kappa cancels out, the pressure gradient cancels out, okay. And what I end up with is into 3n plus 1 by n whole power n. Okay. Numerator I have r by 2. Okay. In the denominator I have 1 over r power n plus 1. Okay. And then in the numerator I have the diameter power n. Okay. D power minus n, the denominator, is 2 times diameter power n. Okay. And I substitute the diameter is equal to 2 times the radius. Okay. I substitute the diameter is equal to 2 times the radius, okay. And you can easily verify that this will be 1 over R e into, okay, there is a factor of 2 here, okay. There is a 1 over 2 k. So, I have to keep this factor of 2. Okay. So, and if you work out the algebra, okay, the final result is going to be equal to 2 by R e into 2 into 3n plus 1 by n whole power n. The factor of 2 in the numerator is because I have a 1 over 2 here, a 1 over 2 here, and a 1 over 2 in the numerator. Therefore, that gives me a factor of 2 in the numerator for the R e. Okay. And then I have r times 1 over r power n plus 1 into d power n. Okay. That gives me a factor of 2 power n, okay, because d is equal to 2 times r, and that factor of d power n is in here. Okay. So, this is the friction factor correlation for the flow of a power law fluid in a pipe. Okay. One can easily verify that this friction factor correlation reduces to what we had for a Newtonian fluid if n is equal to 1. Okay. For n is equal to 1, the friction factor is equal to 2 by R e into 2 into 3n plus 1, n is equal to 1, this is into 4 divided by 1 whole power 1, okay, is equal to 16 by R e. Okay. So, the Newtonian fluid is a special case of this power law fluid, okay, for the flow in a pipe. Okay. So, this Newtonian fluid is a special case for the flow of a power law fluid in a pipe. Yeah. So, I have shown you 2 examples. In the first one, we had actually solved a problem of how the height in a tank changes as the due to a pressure gradient, where we had 2 tanks connected by a pipe, and we had applied the laminar flow pressure profile for the delta P by L across these 2, okay, and equated that to the difference in the hydrostatic heads. And based upon that, we got the time scale for the transfer of fluid from one pipe to the other, and we had also got verified that the Reynolds number for the flow in a pipe is less than 2100. And then we had got the friction factor for a power law fluid. Okay. A power law fluid is one where the relationship between the stress and the strain rate is not linear. Okay. The relationship between the stress and the strain rate is not linear. And but this was a well defined relationship between the stress and the strain rate, and based upon that we could calculate the velocity profile. Okay. This was the velocity profile that we had calculated, and which satisfied the boundary conditions both at the center, that the gradient is equal to 0, and at the wall of the pipe, okay, where the velocity is equal to 0. We had calculated the maximum velocity and the average velocity. Okay. And based upon that, we had calculated the relationship between the friction factor and the Reynolds number. So, as I told you, the flow in a pipe is laminar for Reynolds number less than about 2100. Okay. When the Reynolds number becomes greater than 2100, okay, the flow becomes what is called turbulent. Okay. Okay. So, this is for Reynolds number less than 2100, the flow is laminar. We just derived what is the velocity profile for a laminar flow. It was a parabolic profile. Vx is equal to 2 V average into 1 minus r square by r square. Okay. That was the velocity in the x direction, and the V average was equal to minus r square by 4 mu dp by dx. The negative sign is because the velocity is positive if the pressure gradient is negative, so that the pressure decreases with the downstream distance. Okay. I am sorry, the V average was 8. Okay. And the maximum velocity at the center was equal to minus r square by 4 mu dp by dx. Okay, that was the average and the maximum velocity for the flow in a pipe. And then we had got the wall shear stress, tau w is equal to minus dp by dx into minus r by 2, or the diameter by 4. Okay. So, all of those things we had derived by solving the conservation equation minus dp by dx plus 1 by r d by dr of r tau xr is equal to 0. Okay. This is valid for when the Reynolds number is less than 2100. Okay. When the Reynolds number exceeds 2100, the flow becomes turbulent. The average velocity, what is called the mean velocity in this case, is more plug like, with a smaller curvature at the center and steeper gradients at the wall in comparison to a laminar flow. Okay. Steeper gradient at the wall in comparison to a laminar flow, a smaller gradient at the center. Okay. This is for a turbulent flow. Okay. This is for Reynolds number greater than 2100. Okay. At each point in the flow, the velocity is in the streamwise direction on average, but there are fluctuations. There are fluctuations in all three directions. So, if I plot the velocity at a particular instant location as a function of time in any direction, Vx say, I will get something that is fluctuating about a non-zero average, okay, where this average value is the velocity, average velocity, the mean velocity at that location. So, the velocity can be decomposed into an average component plus a fluctuating component. Okay. So, if I subtract out the average velocity V bar, okay, from Vx, I will get the fluctuating part. The flow consists of what are called turbulent eddies, okay, which are parcels of fluid in correlated motion, and the eddies have a range of sizes, all the way from the diameter of the pipe to the smallest scale, which we will discuss a little later. Okay. From the largest scale eddies are comparable to the diameter of the pipe, and the small scale eddies are much smaller. You have fluctuations in all three directions. Okay. So, for example, if I were to plot Vy, okay, in the y direction, for example, perpendicular, okay, so this is x and this is y perpendicular to the plane, that would also fluctuate. Okay. That would also fluctuate. Similarly, Vz in the third perpendicular direction, that would also fluctuate. Okay. So, I am assuming a coordinate system here x, y and z. Okay. Z is vertical and y is into the plane and x is the horizontal direction. So, all of these would fluctuate in position and time, and the model for the shear stress that we had seen was of the form the Reynolds stress, okay, tau x let us say z r is equal to minus rho times V x prime V z prime. Okay. This is the transport of momentum due to the convective transport, okay, due to convection due to the fluid velocity fluctuations. The mean shear stress is the shear stress due to the mean velocity. In addition, since you have fluctuations in all three directions at a given location, there is transport of momentum in all three directions due to convective effects. And the models that are used for this are of the form tau x z r is equal to an eddy viscosity, okay, into d v x bar by d z. Okay. Okay, that is the model that is used for the Reynolds stress or the shear stress due to the fluid velocity fluctuations. All of these are just revision of what we had already done when we studied dispersion and diffusion. And I told you at that time that the eddy viscosity should be considered as a flow property, not as a fluid viscosity, not as a fluid property. The molecular viscosity is a fluid property. It is fixed for a particular fluid under certain particular conditions of temperature and pressure. So, if you take a fluid with a particular temperature and pressure, the viscosity is a constant quantity at that same temperature and pressure. It is a molecular properties. It depends upon the molecular diameter and so on, the mean free path and the fluctuating velocities. So, the molecular viscosity is a fluid property. The eddy viscosity is a flow property, because it is the flow that is convecting momentum across the flow, these parcels of fluid that are convecting momentum. So, because it is a convective effect, it does not depend upon the molecular viscosity, it depends only upon the particular flow, that is the flow Reynolds number will basically determine what is the eddy viscosity. And the models for the eddy viscosity are what are called the mixing length. Okay. The eddy viscosity is equal to rho times a turbulent fluctuating velocity times a turbulent fluctuating velocity times what is called a mixing length. Okay. Mixing length is the length scale over which these eddies transport momentum before their velocity gets uncorrelated. So, these eddies are parcels of fluid which form and then which are correlated for some period of time. Okay. So, they are not correlated permanently, they are correlated for some period of time, which is called the what is called the eddy turnover time. Okay. So, they are correlated for some period of time, and so they appear and they disappear in the flow. Okay. They are spontaneously created by the flow turbulence. V prime is the characteristic velocity of these eddies, and L is the characteristic length of these eddies. Okay. So, these were the characteristics of a turbulent flow that we had seen when we talked about diffusion and dispersion. Turbulent dispersion is due to correlated parcels of motion called eddies, which are moving in all three directions. And these are spontaneously generated in a turbulent flow. Okay. You do not need to have an external disturbance in order to generate these kinds of flow structures. So, in that sense, laminar and turbulent flows are very different. Okay. They have very different characteristics, and because of that this transition is a very important is a central concept in turbulent flows, the transition between a laminar and turbulent flow. we had discussed this both in the context of flow through conduits and the flow around particles and the flow past slender bodies. For the flow through a pipe and channel and so on, this occurs at a particular value of the Reynolds number. For the flow past a flat plate, we had discussed that it takes place at a certain downstream distance from the leading edge. If the distance is longer than the distance for a turbulent flow, where the flow past a flat plate is laminar for some period of time, and then it undergoes a transition to turbulence, okay, where x is a streamwise distance and the velocity here is the streamwise velocity, the free stream velocity. And this occurs where Rex is equal to 5 into 10 power 5. Okay. This is equal to rho x times V free stream by the viscosity. Okay. That is a turbulent flow in the flow past a flat plate. And we are also seeing the flow around a particle where there were turbulence formed in the wake when the Reynolds number increased beyond about 400 or so. Okay. Beyond about between 400 and 4000 you had oscillating vortices being shed at the rear side, and above about 4000 the flow became turbulent on the downstream side. So, this is a summary of our discussion of turbulence so far when we looked at the different flow regimes in different geometries. Now, we will take a closer look at the fluid turbulence specifically in a pipe. Okay. And there are two questions here. One is, why does it become turbulent? And the second is, what is the structure of the turbulent flow, or the variation in the velocity and so on in the turbulent flow across the pipe cross section. How do these vary? Okay. First question is, why does the flow become turbulent in the first place? Okay. Especially at a Reynolds number greater than 2100. What is it about this Reynolds number of 2100 that causes the flow to become turbulent? This is a question that has not yet been answered, and it is a subject of active research still. What is it that happens at a Reynolds number of 2100 that makes the flow go turbulent? There are other geometries, such as, for example, the other flows, rotating flows, and temperature flows driven by temperature variation, natural convection, where a similar question arises: is the flow laminar or turbulent, and what determines whether the flow is turbulent or not? So, these two issues, what makes the flow go turbulent and what is the nature of the flow after it becomes turbulent? These are two issues that I will try to address in the next few lectures when we discuss turbulent flows in a channel. So far I have discussed laminar flows, got for you the friction factor relationship, solved a couple of problems where we calculated the friction factor and used it for determining the flow rate and thereby the change in the height of a tank, for example, which is connected by a pipe. Turbulent flows and the reason for turbulence and the structure of turbulent flows we will start discussing in the next lecture. I will see you then.